So now we're going to talk about intrinsic semiconductors. Intrinsic semiconductors have a band gap where the valence band is completely filled and there's no impurities. So at absolute zero, it looks like this. If we then click on this, and we can watch what happens as we start to promote electrons. Let me grab this. So again, at absolute zero, we have nothing in the conduction band. As we increase temperature a little bit, we see that we start to promote some electrons from the valence band to the conduction band. That's because you have the Maxwell-Boltzmann tail to the Fermi-Dirac statistics, that as you promote some electrons at the top or at the Fermi level, they get pushed up into the conduction band. So we use the tail, this exponential tail, that some tiny fraction at a finite temperature can actually get up to the conduction band. As we increase adding temperature, a medium temperature, the number of electrons that are promoted end up in the conduction band. And now these electrons, because there's lots of available states for these electrons to hang out in, they can start to flow. As you go up to still higher temperatures, you pump even more electrons in. This is an exponential process. That's why the conductivity does nothing, nothing, nothing. Then at a certain temperature, it climbs exponentially, and you turn a semiconductor basically into a metal. How's that work with our parking lot analogy? So here we are at absolute zero. All the cars are stuck in this bottom layer. As you start to increase the temperature, at some point, so at some temperature, you start to promote a car up. And once it's up there, it can start driving around up there. And notice that the hole starts to move in the opposite direction. So this parking lot analogy still works. You just need the elevator to pump it up here. And that's how we think about getting electrons from the valence band to the conduction band.